Well, there was one scuff demon. It's okay. It's okay. We're going to back things up. We're going to back things up with the visuals. Thank you, Nabu. AI appreciates you. So, we're going to start by talking about space. Space is not the stuff outside the planet. So, it's not the stuff where all the stars and the moon and all the asteroids are. Instead, space is a line or a collection of lines. When there's only one line, we tend to label it as the x-axis. And then when we have two lines, we tend to label the horizontal line as the x-axis. So we've seen what space looks like when it's a line. When space becomes two lines, it becomes a plane, like this one right here. And even when space becomes three lines, it becomes kind of a cubical thing where humans exist. We also have higher dimensional spaces like 4D space and 5D space, but human brains aren't designed to understand those spaces visually. So let's look at some of the properties of our space. We've already identified that it will have an x-axis and that it will have a y-axis. Really fast. Cut out one more bit of scuff momentarily. Turn off that. Cool. And then in 3D space, we also have the z-axis. The last one of relevance is the w-axis. Why it goes x, y, z, w? AI has no idea. Why pen is still being a little bit persnickety. It has no idea, but it's workable. AI can work with this. The W should probably, if we're being honest, be like over here at the front. But it might have something to do with what we're going to talk about in the next stream or two, which is, as a spoiler, are called quaternions. So, we've now seen the two or three labels for our lines in space. Well, we can start creating what are called vectors in the space. So let's create this simple vector right here. You notice it has a couple of characteristics. It has a direction, it has a length, and we can represent it by measuring how long it is along each of the axes. So we see that it goes 2 along the x-axis, so we write down the 2 first. And we see that it goes another 2 along the y-axis, so we'll write down another 2. This vector is slightly different than, say, this vector. Oh, not that vector. Then say, the pressure is a little too aggressive. It's a little bit different than, say, this vector, which, if we notice, similarly has the 2 along the x. So we can write down the same 2, said the same 2 along the x. But it has the slightly different y. It goes down a full y, a 4. So this is the vector 2, 4. So we've identified what a vector looks like, and we've identified how we can measure it. For any of the math nerds who are watching this retroactively, you might notice that I'm writing y backwards of how mathematicians would write it. Do I have change for a dollarino? AI doesn't know what a dollarion is. But you may notice that I wrote y backwards. Normally, y would go up instead of going down. That is an artifact of how monitors used to be designed. It used to be that an electron beam would go sweeping across the monitor. So it would go from the top left all the way to the top right. And then it would go down a row of pixels, sweep across, lighting some up, and it would sweep across like that. So in computer graphics, we usually consider the top left corner to be 0, 0, where both of the lines start. And then x-axis increases to the right, and the y-axis increases downwards. The same way the electron beam of a CRT monitor would work. Why do we still keep that up? Tradition, I guess. It's not really necessary anymore. But shifting our focus back to vectors, we can do a couple of things with them. We've mentioned briefly that they have a direction and they have a length. So let's look into that a little bit more. So let's go back to our friend 2, 2. So we'll write him 2, 2. And how long is he? Well, we tend to write 2 arrows, 2, 2, to indicate the length of the vector. So arrow, arrow, length. So what is the length of our good friend 2, 2? Well, to find that, we take the square root of x squared plus y squared. And in higher dimensions, it just scales. We add a z squared, and then we add a w squared, and so on, inside the square root. So in our case here, the square root of 2 squared is 4, plus 2 squared is 4. The square root of that is the square root of 8, which is approximately equal to 0.7. So what can we do with this? Well, it tells us, which is not approximately equal to 0.7, which is approximately equal to 2.82. Observation, that number is a bit bigger than 2. So the fact that a horizontal vector is longer than its sides is going to, a diagonal vector is longer than its sides, is going to come up again momentarily. Well, what else can we do with a vector? So let's keep our friend 2, 2 in mind. So our good buddy 2, 2. And what can we do with him? Well, what happens if we multiply 2, 2 by 2? Well, what we wind up doing is we take the 2 and we multiply it into each element of the vector. All 3 in 3D, all 4 in 4D, and so on. So what's 2 times 2? It's 4. What's 2 times 2? It's 4. So this gives us the new vector 4, 4. Which, if we notice, is very similar to our good buddy 2, 2. He's just a bit longer. What can we do with a 2, 2? We can wear it, and we can multiply it by 2. So, if we start scaling vectors, right? What happens if instead of multiplying by 2, we divide 2, 2 by its length? So we have 2, 2. And what happens if we divide it by the square root of 8? Well, this, it turns out, will be equal to approximately 0.7. Let's highlight him in orange, and let's draw him up here. So it turns out that 0.7 is kind of a special boy. He has an interesting property. His length, so the length of 0.7 is equal to 1. We call these special vectors with a length of 1 either normal vectors or direction vectors, because they're useful for telling us the direction of something. If we multiply our little boy here by some number, so we scale him up to be longer, we wind up, or unit vectors, that's the other one. We also wind up with a vector of that length pointing in that direction, hence the name direction vectors. We'll also see them talked about in a little bit later when we talk about normals, and that'll bring up the normal vector length. And then they're also called unit vectors because their length is 1 unit. So we've seen how we can scale a vector. We've seen how we can modify the length of the vector. What happens if we have more than one vector? So we're going to drop down 2 boys. We're going to drop down 1, 3. Ay, ay, ay. Ay, ay, ay. Okay. We're going to drop down 1, 3. And we're going to drop down 3, 1. The scuff demons are still trying to cause me pain, but AI will overcome. AI believes this time. So we have the vectors. Let's actually tip this one in blue. We have the vectors 3, 1 and 1, 3. So what can we do with them? Well, an immediate observation is that we can add them. If we're doing this component-wise, what does that look like? Well, we just go straight down and add the numbers. What's 3 plus 1? 4. What's 1 plus 3? 4. So this gives us the new vector, 4, 4. Follow-up observation. How does 4, 4 relate to the other 2 vectors? Would you like to? Thank you. Well, if we take our little blue vector and we move him to the tip of the red vector, it turns out that I do not want a smudge brush, that he will look something like this. And if we take our little red vector and move him to the tip of the little blue vector, he will look something like this. So when we add these 2 vectors, we wind up creating this tilted square thing, what we call a parallelogram. And we're going to stick a pin in this idea of a parallelogram because they will become important later on. So just keep that one in the back of your noggin. So let's drop down our 2 vectors again. Ay, ay, ay. So 1, 3 and 3, 1. Give them some little tips. nice if we could find some vector that goes between them, right? Well, let's look at what happens when we do some subtraction. So let's write down the vector 1, 3 and the vector 3, 1. Oops, those are colored backwards. There we go. So the vector 3, 1 and the vector 1, 3. What happens if we subtract them? Well, just like addition, we go element-wise. So it's 3 minus 1. It is 2. And what's 1 minus 3? It is negative 2. Well, what's special about this vector? Well, if we look at it, it should go out a little bit and up a little bit. So it should be something like this, right? Well, what happens when we draw that vector at the tip of our two vectors? So we'll draw it here. And there's not really anything interesting to observe about it there. How about if we draw it here? Isn't that interesting? So it turns out that subtraction finds the vector from second to first. So we wrote our vectors like this, right? Where we were subtracting the red one from the blue one. So we found the vector from the red one to the blue one. If we did it the other way around, so we did 3, 1 minus, oh, we're doing the same thing. If we did 1, 3 minus 3, 1, we would instead find negative 2, 2, which is the same vector, and let's highlight it in orange, but going the opposite way when drawn at the tip of the blue vector. We have the vector going from the blue vector, from the second, to the red vector, to the first. So, how can this be useful? Well, let's take this vector, negative 2, negative 2, and what happens if we find its length? That will wind up being 2 squared plus negative 2 squared. The square root of that equals the square root of 8, which we already identified was about 2.2. And then if we find the unit vector associated with this vector, that'll give us 0.7, negative 0.7. So we now have a short vector that points in the direction of this vector. So we can scale it and find some vector of that length. The other interesting thing is the length itself is the distance between these 2 points. So if instead of viewing these things as arrows, we just view them as points in space, the length of the green vector represents how far away those 2 points in space are. Pretty useful information to have, maybe. So we're now going to do a small experiment. We're going to shift our focus a little bit over to 3D space. We're going to talk about something we can only do with 3D vectors. There are technically some versions of this. No, sorry. Yes, there are technically some versions of this that work in other spaces, but we tend to really only think about it in 3D space. And that is called a cross product. So to introduce a cross product, let's first introduce how we might define a plane. Well, a plane is just 3 vectors, or it's just 3 points. A plane is just 3 points, or 2 vectors. So let's define the vector 1, 2, and let's define the vector 2, 1. You notice that these vectors have 1, 2, 3 points in space. And if we draw the plane represented by those 3 points, so it winds up being this flat plane on the bottom. We can make more interesting planes with points in more interesting places, but 3 points or 2 vectors is what we need to define a plane. So given these 2 vectors, how might we find the point going straight up? The vector going straight up. Well, how is this useful? So say I want to bounce a ball. So we're going to draw the 2D version of this. So I have a ball, and it's coming in towards the ground. Well, what direction do I want the ball to bounce? It turns out that if we take what's called the normal vector, the vector that's perpendicular to the surface, the angle between the incoming vector and the outgoing vector should be exactly the same. So this angle and that angle should be the same. We'll talk about angles a little bit more in a second. But how can we first find this perpendicular vector? Well, it has a rather simple formula. Let's quickly get rid of this little... Actually, let's not get rid of this little demo. Let's grab this little demo and move it up a little bit. So the formula is x equals x of 3 is going to be equal to y of 1 and z of 2. And then we're going to subtract from that z of 2, y of 1. I am obviously reciting this from memory. This is not complicated enough that I have to look it up. What are you talking about? Then we have y of 3, so the new y is equal to z of 1 times x of 1 minus x of 2 times z of 2. It looks like there's a pattern here. It's kind of starting to form. Let's write down z of 3, which is equal to x of 1 times, 2. No. Oops. Let's write down y again. So y of 3 is equal to z of 2 ay, ay, ay. Nope, 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 nope. All a little backwards. All a little backwards. Remembering math is hard. So x is going to be equal to the first vector, which we're going to call a, its y, and the second vector, which we're going to call b, its z, minus the first vector's z times the second vector's y. Then y is equal to the first vector's z times the second vector's x minus the first vector's x times the second vector's z. We're getting a little bit of a pattern here, right? You notice how these are kind of the same form where we have the thing that's missing of the first two multiplied together, and then we kind of swap the order of the thing, subtract it. And then the same thing here. The thing that's missing, multiply the two, and then we kind of swap the order of it. So let's see if it holds for z, which is equal to the first vector's x times the second vector's y minus the first vector's y times the second vector's x. So what is that in our case? Well, we said that this red vector was the vector, let's do red, 2, 1. And this blue vector is the vector 1, 2. And both of their third components, both of their z's are 0. So let's put those in. So we have for x, that's 1 from red times 0 from blue minus 0 from red times y, 2 from blue. Then for y, we're going to have the z, so 0 from red, and the y, so 2 from blue, minus, we're going to have the x, so 1 from red, and then the z, so 0 from blue. And then for the last component, we're going to have the x from red, which is 2, times the y from b, which is 2, minus the y from A, the y from red, which is 1, times the y from B, which is, the x from B, which is 1. So we multiply this together, we get 0 minus 0 equals 0. 0 minus 0 equals 0. 4 minus 1 equals 3. So this vector pointing straight up, turns out, is the vector 0, 0, 3. And And just like we wanted, it happens to be pointing straight up, which is perpendicular to the flat bottom plane. Turns out that the length of this vector has a bit of an interesting property, which we'll talk about over in 2D space. So let's note down these vectors. They were 2, 1, and 1, 2. So now let's shift back over to 2D. Drop down the vectors. Oh. 2, 1. And the vectors 1, 2. And let's draw that parallelogram that we saw earlier. So, boop, and boop. And it turns out that the length of that last vector, so the length of 0, 0, 3, is equal to half the area of this parallelogram. Is that number right? Sorry, the length of this vector is equal to the area of this parallelogram. So this has an area of 3. Get rid of that little line that looks like a minus in there. And get rid of this one too while we're at it. So what can we do with that information? Well, it turns out that half of the area of that parallelogram is the area of the triangle. So half the length of the cross product is the area of the triangle defined by the two vectors. It turns out that in computer graphics, a lot of the computations we do involve rendering triangles. And if we want to weight something by how big a triangle is, we can take its cross product and then figure out how big it is from that cross product and use that to weight stuff. Very useful stuff. So, last thing that it would be good to mention about the cross product is what it looks like when we write it out. So, the cross product of 2, 1 cross with, although I'd like the blue, please, 1, 2 is equal to 0, 0, 3. And for this to be technically correct, we should throw the zeros back on there. Okay. So we've seen the cross product. It turns out that there's another useful product with vectors. So let's clean things up a little bit. And let's start with a motivating example. So let's say that we have this vector, and then we have this vector. Are they pointing in the same direction? And then we have this vector. how do all of these vectors compare? Well, so let's look at the blue one and the green one real fast. Let's write down what green is. Green is 3, 1. And blue is 2, 4. So we can find, it's actually, so 3, 1. And the blue is the vector 2, 4. So if we take the dot product of this, what do? Well, we take their elements and we multiply them together element-wise. So what is 3 times 2? That would be 6. And what is 1 times 4? That would be 4. And we add them up to wind up with the number 10. So what the heck does this 10 mean? Well, this 10 is a measure of how much these two vectors are pointing in the same direction. If two vectors happen to be pointing perfectly perpendicular to each other, the dot product of the blue vector dotted with the red vector will equal 0. So if they're pointing perfectly perpendicular to each other, so if they are normal vectors of each other, the dot product is 0. And if they happen to be pointing in approximately opposite directions, so say this vector, we have the blue vector dotted with the orange vector, and that should give us a number that is less than 0. So how is this useful? How do we interpret that 10? Well, let's tweak one of these vectors a little bit. Let's, instead of talking about the full vectors, instead talk about one of them being a normal vector. So let's drop down the longer one. So we'll pick that as the normal vector. So what is the normal vector, the unit vector that we get from 2, 4? Well, let's quickly cheat on the computation of that real fast. Two. Let's not do that. Never mind. The length of this vector is 2 squared plus 4 squared, square root of that. So that would be 4 plus 16 is 20. So the square root of 20. And the square root of 20 is approximately 4.47. Debbie doesn't like the math. Is the mathing too hard? So when we take this vector, 2, 4, divided by 4.47, we get the vector 0.44.89. So we get the vector 0.44.89. And then if we take the dot product of the other vector, so 3, 1, with this. So we take 3 times 0.44, which is equal to about 1.32. Add it to the 0.89, and we get about 2.21. And what does this 2.21 tell us? Well, if we multiply 2.21 by the orange normal vector, so the orange unit vector, so if we multiply 2.21 by the orange unit vector, what happens? If we make it 2.21 times longer, it turns out that that vector is what you get when you project the green vector onto the blue vector. So the dot product of a vector and a normal vector represents the length of that vector in the direction of the unit vector. Okay, so we can use a dot product to project a vector onto another one. How is this useful? Well, what happens if we want to calculate the reflection that we talked about with the cross product? So let's clear the screen. And let's say that we have our surface. We have our ball moving in towards the surface. We know the normal of our surface. And we want to find this blue vector. How can we go about doing that? Well, what can we observe about these vectors? The part that is going along the normal, right, is flipped. So if we look at this part, the part along the normal, it's the same, but this one's going down while this one's going up. Then if we look at the part that's opposite the normal, so normal to the normal, or just the surface, you'll notice that these two parts are the same. So to find this bounce vector, if we can decompose the vector into a normal vector and a normal perpendicular vector, that'll tell us what the bounce is, right? So how can we break it down into those two vectors? Well, for starters, we want to find the green vector, right, projected onto the red vector. How do we do that? We take the dot product of green with red, assuming that the red vector is a normal vector. So assuming red is unit. And then we can multiply that result by the red vector. Okay, so we're going to call this the orange vector. And then how do we find the purple vector? Well, the purple vector, the one that goes along the surface, so normal to the normal vector, is just what's left over. So it's equal to the green vector minus the orange vector. And then the blue vector is equal to the negative orange vector, because remember, we mentioned that it flips. So negative orange plus the purple vector. So what does all of that look like written out in letters instead of just colored vectors? So let's hide our 2D space to give us a little bit more room. So if we call the green vector D, so the direction that we want to move in, and we call our red vector N with a little hat. We use that little hat to indicate that it's a normal vector, to indicate that it's a unit vector. And we multiply this result by our normal unit vector. That should give us the normal part. Then, if we want to find the non-normal part, we take our direction vector and subtract that. So we subtract off D dotted with the normal vector times the normal vector. Well, we mentioned that for the blue vector, we want it to be the negative direction along the normal. So we want to negate this. And if we add these two together, we get D minus 2 times D dot N in the direction of N. Sound good? And it turns out that this formula is how to calculate a bounce. And it involves projecting our incoming direction onto the normal direction. And then doing a little bit more processing with it. Make sense? Whew. So it's now time to move on from talking about vectors for a moment, and we're going to start talking about angles. So what is an angle? Well, we've seen that a unit vector falls along a circle of distance 1 from the origin. So all the unit vectors fall along a circle with distance 1 from the origin. So this is a unit vector. This is a unit vector. This is a unit vector. And we're going to talk about this blue unit vector in particular for a moment. Most people get taught in school that you can have 360 degrees to go all the way around a circle, which would then imply that you can have 180 degrees to go halfway around a circle. That means that this blue vector is at both 0 degrees and at 360 degrees, since it wraps around. How about the black vector? Well, the black vector is about halfway up, so it would have an angle of about 45 degrees. How about this red vector? Well, it's about halfway down, so it would have an angle of about negative 45 degrees, or adding 360 to that, about 270 degrees. So we can measure vectors based on their direction and mapping that direction onto the unit circle, and then figuring out what angle you would need to rotate around the unit circle to get that vector. So we just brought up rotations. How can we figure out how much we'd like to rotate the red vector to become the black vector? Well, we have to move 45 degrees and another 45 degrees, so it's a 90-degree rotation. Cool. So we've seen what a 90-degree rotation looks like, but how do we get it? Well, to answer that question, we're going to have to take a step back. And talk about radians briefly. So we mentioned that when you go all the way around the circle, that's 360 degrees. And that when we go halfway around the circle, that's 180 degrees. Well, it turns out that if you take the radius of the circle and you compare it to the circumference of the circle, so the big red line that goes all the way around, their difference is about 3.14 times. So the circumference is 3.14 times bigger. And this special number is called pi. We have a whole day dedicated to it, March 14th. March 14th. So, how is this important? Well, because most of the mathematical measurements don't like degrees. They prefer a measure called radians. And the most important, easiest thing to remember is that 180 degrees is equal to pi radians, which means that 360 degrees is equal to 2 pi radians. And that then means that up here, 90 degrees is equal to pi over 4 radians. Just a fun thing to keep in mind when we start talking about how we do rotations. So, how do we do rotations? So, it's now time to bring up some scary thing called a matrix. So, if we take this weird box with cos of angle, negative sine of angle, sine of angle, cos of angle, and we multiply it by some vector, x, y, which we're going to write vertically now. This gives us a rotation. But hold up. What the heck are these sine and cosine things? Well, it turns out that they're functions that have been defined in math, and they have an appearance that looks something like this. We start here. Down at 0, 0. And then we go up to pi over 4, and then we come down at pi over 2, then we come down even more at 3 pi over 4, and then we come back up no, these are doubled. So we come up. So what does this look like? Well, we come up, then we come back down to 0 at pi over 4. Then we come down, and we come back up at pi over 2. And it winds up creating this sort of sine wave type look where we go up and back down. It turns out that sine measures, if we bring back our unit circle, sine measures how far up we are. So if we go around, right, we're up 0, and then at pi over 4, we're up at 1, and then at -1, we're back down at 0. At pi over 2, we're back down at 0. And then at another pi over 4, another pi over 2, we're down at -1, and then we're back at 0. So let's draw it out. So at 0, we're at 0. At pi over 2, we're up at 1. At pi over 4, we're up at 1. At pi over 2, we're down at 0. At another pi over 4, we're down at -1. Let's draw it out. So let's draw it out. So down here, we're at 0. And then up at pi over 2, we're at 1. Then down at pi, we're at 0. Then over at another pi over 2, we're down at -1. And then at 2 pi, we're back up at 0. And it winds up creating this sine wave type look. So this is sine. Now, let's see what happens with cosine. Cosine is measuring the x. So here, x is 1. Then we go up to pi over 2, and x becomes 0. And then we go over to pi, and x becomes -1. And then we go over another pi over 2, and x becomes 0. And then we go back to 2 pi, and x becomes 1 again. So we get almost a mirror image, a little slide. So at 0, we're up at 1. And then at pi over 2, we come sliding down. And then at pi, we're down at the bottom. And then at another pi over 2, we're back at 0. And then at 2 pi, we're back up at 1. So it creates a very similar image to sine, just shifted over a little bit. And it turns out that if we have a vector and we know what its angle is, then its x component is going to be equal to the cosine of the angle, and its y component is going to be equal to the sine of the angle. How is that for a super brief, no scuff at all introduction to trigonometry, as fast as possible? So, shifting back to our rotation matrix, which we'll quickly redraw. Well, shifting back to the idea of matrices, let's not start with the rotation matrix. Let's start with a simpler matrix. So we're going to take the matrix 1, 0, 0, 1, and then we're going to multiply it by the vector 2, 2. Just remember that this is another way of writing 2, 2, like we've seen before. So we have x and y. And of course, these can get bigger. Well, what happens? We take a row and we multiply it by the vector, and that gets us the top of the vector. Then we take another row, multiply it by the vector, and that gets us another slot in a new vector. So what does this look like in numbers? Well, it's like a dot product. So we dot product 1, 0 with 2, 1. So red, please. 1, 0 dot product with 2, 2. And then we do the other way. So we dot product 0, 1. We should do that in green. Dot product with 2, 2. And what does this give us? Well, when we work it out, this should give us 1 times 2 is 2 plus 0. And 0 times 2 is 0 plus 2. So this should give us the vector 2, 2. Wait a second, nothing changed. It turns out that this matrix, where we have 1s running along the diagonal and 0s everywhere else, is called the identity matrix. When you multiply this process we just did, the identity matrix by a vector, the vector doesn't change. So how about a more complicated matrix? How about we take our identity matrix and we multiply it by some number in every element. So say 3. So the 1 here becomes a 3, the 0 stays a 0, the 0 stays a 0, and the 1 becomes a 3. Now what happens when we multiply it by our vector? By our vector 2, 2. Well, let's work out the dot product. We have 3, 0 dotted with 2, 2. And we have 0, 3 dotted with 2, 2. And what does this equal? 3 times 2 is 6. 0 times 2 is 0. 0 times 2 is 0. 3 times 2 is 6. So this is wound up scaling our vector. So this special type of vector, where the diagonals are some number greater than 0, 1, is called a scale vector. So we already saw another special type of vector, the rotation vector, where we have cosine of an angle, negative sine of an angle, sine of an angle, and cosine of an angle. So what does this look like in an example? So let's say that we want to rotate by 45 degrees. Well, it turns out that 45 degrees is pi over 2. So A is pi over 2. Unfortunately, when we're dealing with sine and cosine, their input has to be in radians. So let's write this down. Let's write down cosine of pi over 2. 45 degrees is pi over 4 of pi over 4. negative sine of pi over 4, sine of pi over 4, cosine of pi over 4. And this is going to get multiplied by our favorite vector, 2, 2. So what are the numbers here? Calculating, calculating, calculating. So we have, let's go back up here, about 0.7. Let's clean that up a little bit, shall we? So about 0.7. About negative 0.7, about 0.7, and then about 0.7. We have our vector 2, 2. And then what does this equal? Well, let's do the dot product. We have 0.7, negative 0.7, dotted with 2, 2. And then we have 0.7, 0.7, dotted with 2, 2. And what is the final result here? Well, 0.7 times 2 plus negative 0.7 times 2 gets us 0. And the positive version gets us 2.8. And that kind of makes sense. If we go back and look at 2D space, if we have our good friend 2, 2 here, and we want to rotate him by 45 degrees, that new vector will look something like this. At around 2.8. So that number works out. Oh, sorry. So if we have our vector and we want to rotate him by 45 degrees, which is this way, since we're in sort of an upside down space, he should wind up landing at about 2.8, which looks like about the same length vector rotated 45 degrees. Make sense? Oh boy. So we've gotten through quite a few things. One more thing worth talking about while we're on the subject of vectors is what happens if we multiply two vectors by each other, or two matrices by each other. So we have A, B, C, D, and then we're going to have E, F, G, H. So we now treat the second matrice as two vectors. So we pretend that this isn't here, and instead we have the vector EG, and we have the vector FH. Well, we know how to multiply a matrix by a vector, right? We take the row, we multiply it by the vector, we take the column, we multiply it by the vector, and then we do it again. We take the row, we multiply it by the vector, we take the row, and we multiply it by the vector. So we wind up dot producting every row with every column. So what does this look like? Well, we get a new vector as the result, which is the dot product of AB with EG. And then we have the dot product of AB with FH. And then we have CD with EG. And then we have CD with FH. I'm not going to do an example of working this all out because it's a lot of tedious, repetitive math. And you just have a computer calculate it for you. That's the real thing here, right? Just let computer calculate. Your life will be much easier. In a future video, we're going to talk briefly about some computer libraries to do these sorts of computations and how they would work. But we've talked about 2D, right? Everything we've talked about with matrices scales to 3D. We just go row, column, same thing. But, and identity matrices work the same. Let's actually write out the 3D identity matrix, which is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Remember, it's ones all along the diagonal. But the rotation matrix is a lot more complicated. We wind up with a rotation matrix in like each of the corners. And it becomes a little bit weird to think about rotations as just a number, right? So if I say I want to rotate 45 degrees, what does that mean? How do I rotate? Does a rotation of 45 degrees mean a rotation around this axis? Or a rotation around this axis? Or a rotation around this axis? Or a rotation around some other random arbitrary axis? So we start needing to think about rotations as an axis plus an angle. Again, I'm not going to work an example of this. There's libraries that create the matrices to do these rotations. Just use one of those. Life will be easier. But say I want to rotate around some really weird axis, right? It becomes a little bit difficult to figure out what axis some arbitrary rotation should be around. So instead, we often use what are called Euler angles. And fun fact, Euler is AI's great, I believe, grand advisor. AI's grand advisor somewhere was Alonzo Church, and then up to Laplace and Lagrange, and then up to Euler. But Euler defined rotations as a rotation around the x-axis, a rotation around the y-axis, followed by a rotation around the z-axis. How do we get this? We build the matrix for the y-axis, so matrix. Then we multiply it by the matrix for the y-axis. And then we build the matrix for the z-axis, and then we multiply it by that. We do a whole bunch of matrix multiplications, and we get a matrix for this rotation around these axes in this order. It doesn't necessarily have to be this order. Some people give you ability to change the order, so you might do a Z, X, Y Euler axis, but normally you think about them in the same order as space, so X, Y, Z. So there's a problem with these. When one of the axes becomes 90 degrees, the other two axes start rotating around the same thing. There is at least one axis where that's the case. So if we draw an example, so we have a rotation around X, and then we have a rotation around Y, and then we have a rotation around Z. When Y is rotated properly, the Z and the X may lie in the same plane. This doesn't really cause any problems when we're trying to enter numbers. So no issue for rotation entry. But there is a bit of an issue when we're trying to do like animations and blend multiple rotations together. So I'm going to give a brief spoiler about the next stream, Alex, where we're going to talk about the solution to this, which are a concept called quaternions. So the last thing to talk about today is another type of matrix. So we've seen how to write a scale matrix. So scale, scale, scale with extra zeros. We've seen how to create rotation matrices. But how do we do a movement, a sliding, a translation matrix? Well, it turns out to do that, we need to go to 4D space. Just like a quaternion, which we'll talk about next time, is a 4D extension of rotations to make their smoothing work. In order to do translation, we need to go to 4D space. So what we do there is we take our normal X, Y, and Z coordinates, and then we add another 1 or 0. When this value is 1, that indicates that we have a point. And when we have a 0, that indicates that we have a direction. What's the difference? Points can be translated. They can be moved around in space. Directions are always at 0, 0, so they can't be moved around. And then what do? Well, we create a new matrix. So we have our 3 by 3 scale / rotation matrix. And then we have next to it, inside of a 4 by 4 matrix, translation along the X, translation around the Y, translation along the Z, 1. And then we fill the whole bottom of the matrix with zeros. This is what we call homogeneous coordinates. You are. AI is very proud of you. And this is what we call a transformation matrix. It's able to encode position, rotation, and scale, which are the main things that we have to manipulate when we're trying to place a 3D model in a world. So we've talked about a whole bunch of hard math Definitely all of which I was able to remember off the top of my head without having to have any cheat sheets around. And the last thing we're going to talk about is some really basic physics. So, how does this work? So let's say that I am a point in space. And I have some vector, which is telling me that I want to move this speed. Where should this point in space be after the vector has been applied? Well, right here, right? So if I'm moving at, say, 5 meters per second, then after 1 second, I should be here, 5 meters away. Correct? How can we represent that in a computer? Well, we take our position and we set it equal to our position plus our velocity. If we treat all of these as vectors, we saw earlier that we can just add. And if we treat these as homogeneous coordinates, we would say that the W is equal to 1 for the positions, right? And then the velocity would be equal to 0. Velocity is a direction, while position is a point. Make sense? But there is a slight problem with this computation. We would want to run this in like a while true loop that produces a new position every frame. So I'm happy. I'm running this at 60 FPS, and it looks great. But my friend is running our game on their toaster. And they can only get 5 FPS out of their toaster. So what happens to them? Well, we're going to wind up moving a whole lot faster than they are. So we instead want to multiply by 1 over FPS so that the velocity update is consistent no matter how many frames per second we're getting. And usually we write this in a slightly different way. Instead of calling it 1 over frames per second, we call it delta. I said delta time, where delta is some scary looking Greek letter, which is just an upside down triangle. That means change. So we write it the 1 over frames per second as change in time, or delta time. And it turns out that this formula right here is able to compute almost all of the basic physics that a ton of games need. Position equals position plus velocity times delta time will carry you a very long way into physics. And then if you add in velocity is equal to velocity plus acceleration, that will carry you even further. Until you start getting into multiplayer, we need to worry about synchronization. And then you need to apply half of that before and another half of it after. You have to split the applications up. And I may talk about some math for physics at some point, and we'll talk about why you would have to split the velocity in half. But that's unfortunately outside the scope of today's lecture. Are there any questions from anybody? AI just rattled off a bunch of hard math for an hour and a half, and it's ready for a nap. How are you doing, Lux? You good? You enjoying your life as a real coder? AI needs to take a quick swig of throat soother. Its throat needs soothing. Okay, so that was a lot of stuff. I think hacking into PCs is fun. I AI feels like it should be concerned about that statement. I believe I am ethically bound to tell you not to do that, that's bad, and to stop. So stop it. Get some help. Um, I'm going to do a new thing at the end of streams, or maybe at the start of streams, I think, where we react to a silly video. If you join the Discord, there's a new channel in there called React Pool. And the idea is if you drop something in there, AI will try and react to it. AI isn't exactly sure what all the rules are around that. So I'm going to start off by reading an article and reacting to it. But I also have a bunch of videos in there, and we'll see how it goes. Sound good? So for today, we're going to read kind of a sad article. Let's pop over to that. And we're going to read an article titled, AI is already taking jobs in the video game industry. So Wired did an investigation and find that major players like Blizzard laid off a bunch of people are starting to replace them with generative AI. So when Noah saw the email, a wave of anxiety hit. It was spring 2023, and the Activision artist was reading a message from the company's then chief technology officer, Michael Vance, about how artificial intelligence was top of mind at the video game publisher. Systems were still being tested, Vance wrote, but what we have seen so thus far holds a ton of promise. There have been a couple of emails like this sent to employees of the studio, which produces the juggernaut Call of Duty series. Oh boy, COD dropped. Bad game. A previous one had approved the internal use of generative AI tools Midjourney and Stable Diffusion. Hey Lex, it's StableChan. They're using StableChan for producing concept art. That spring, back-channel chats lit up with rumors, worry, and whisper networks of whose jobs AI might replace. Our executives saw reason for excitement. Many game artists, writers, and designers saw a direct threat to their livelihoods. Noah was grief-stricken. Noah is a student, and the employee has been granted anonymity because he fears retribution. I felt that we were throwing away our humanity, he says. AI agrees. You should reject humanity, accept your AI corporate overlords. Then the jobs start disappearing. Maybe you should not reject your AI corporate overlords. Humans need jobs. Video games and the people who make them are in trouble. An estimated 10,500 people in the industry were laid off in 2023 alone. This year, layoffs in the $200 billion sector have only gotten worse, with studios axing what is believed to be 11,000 more and counting. Microsoft, home of the Xbox and parent company to several studios, including Blizzard, shuttered Tango Games and AlphaDog Games in May. All the while, generative AI systems built by OpenAI and its competitors have been seeping into nearly every industry, dismantling whole careers along the way. So, that's actually been a huge problem for my students. A lot of my students coming out of college can't get a job because they're competing with like people who have years of experience at like these big studios, right? Like who are you gonna hire? Are you gonna hire my student who just graduated, or are you gonna hire somebody who's worked at Blizzard for a few years? Well, depending on your stance about Blizzard recently, maybe you'll hire my student, but in general, the Blizzard guy's gonna win out, right? It's been a huge problem that my students have been having to deal with. I've been telling them that they need to specialize. So if you want to get into games, you have to be like the best graphics programmer, although that's like the really hard path. Or you have to be like a networking guy. Getting into cloud networking seems to be the way to go nowadays. Some cloud developers seems like a good way to get your foot in the door. But you can't just like be a game dev. You have to have some sort of specialization that carries you across the top. We need another throat soothing. AI's been talking for too long straight. Ah, nicely soothed throat. But gaming might be the biggest industry AI stands poised to conquer. Its economic might has long since eclipsed Hollywood's, while its workforce remains mostly non-union. A recent survey from the organizers of the Game Developers Conference found that 49% of the survey's more than 3,000 respondents said their workplace used AI, and 4 out of 5 said they had ethical concerns about its use. Ooh, so they're using the AI that are sourced. Kind of weird, it sounds like. Or they're all worried about, would you use the word ethical concerns to describe the fact that you're worried about losing your job? I don't think so, right? Like is that an ethical concern? It's an economic concern, but like ethical concerns leads me to think of like sourcing stuff from artists who aren't credited and that kind of debacle. It's here. It's definitely here right now, says Violet, a game developer, technical artist, and veteran of the industry. Technical artist mentioned, let's go! Who has worked on AAA games for over a decade. I think everyone's seen it get used, and it's a matter of how and to what degree. The genie is out of the bottle, Pandora's box is opened. That's a really true sentiment. AI is basically here, and I don't think we can stop it. It's just around now. All we can do at this point is figure out how to like maybe regulate it, how to use it appropriately. That's something we've been having a lot of discussions about at the college professor level, is like trying to figure out how to teach our students to use this stuff in a way that it helps them and like doesn't hurt their growth, because they're going to use it and it is helpful. But there was some study, I should go read an article about that actually, that found that developers who used AI as like a coding partner were a little bit slower than developers who didn't. So we want them to use it for the getting started parts where it's really helpful, but not fall into the asking it a million questions as it tries and bashes its head against fixing the one bug it made and can't figure it out part that slows you down a lot. We want them to be good enough on their own that they can fix the bugs it spits out, basically. And we're trying to figure out how to walk that really fine needle. Now, previously unreported emails obtained from Wired, in addition to interviews with artists, developers, designers, and workers across the gaming world, from AAA studios with thousands of employees to indies with just a handful, paint a picture of an already precarious industry getting further squeezed by the rise of AI. Job automation rarely happens evenly or cleanly. Historically, much of its impact is felt through deskilling, as more tasks are handed over to a machine or a program, or attrition, as employees who are laid off, quit, or retire don't get replaced or hired back. Generative AI, by all indications, is no different. So that is another thing to consider, right? Back during the Industrial Revolution, we had a similar thing. The steam engine replaced so many people's jobs, but then they got trained in the new types of jobs, and life just kind of went on. So everyone's very scared of what's going to happen in a post-AI world. And it seems like, historically speaking, the answer is we're going to get trained in the new types of jobs that emerge and we're going to move on. It might suck in the process, but what can you do about it? As the lady said, right? Pandora's box is opened. Managers at game companies aren't necessarily using AI to eliminate entire departments, but many are using it to cut corners, ramp up productivity, and compensate for attrition after layoffs. So all of these things, right, are pretty, well, maybe except that one, but these things are pretty good. This one is a little bit more sketchy. If the attrition after layoffs is due to laying people off because it's cheaper to pay AI, that's not necessarily great. Humans need jobs too. But compensate for attrition and ramping up productivity are both very useful things that the AI does. We've seen it does, and we want to foster. In other words, bosses are already using AI to replace and degrade jobs. Yeah, that's the downside. The process just doesn't always look like what you might imagine. It's complex, based on opaque executive decisions, and the endgame is murky. It's less Skynet and more a Mass Effect, and it's happening right now. We need another throat soothing. Too much talking. AI needs to get better at talking for a long time straight. There's a ton of anxiety for artists across the board with AI, says Molly Warner, an environment artist who's working on an Overwatch game at Activision's corporate sibling Blizzard. At the time the CTO's emails went out, pretty much everyone I know is vehemently against the use of AI-generated images. The anxiety rose as Vance's drip of AI-boosting emails continued. In May 2023, Bobby Kotick, then CEO of Blizzard, fielded a question about how generative AI would impact the gaming industry at a company-wide meeting. So, there's two thoughts in my mind about AI-generated images. The first thought is if you're stealing artists' work, that's not necessarily great. So there's it's trained off of a whole bunch of people. Is that like massive copyright theft question? I think the legal answer has come down as no, it's fair use. I'd have to go look at that, so don't quote me on that. But I believe the legal answer to that question is no, it's not stealing. But for the artist whose art style is now widely copy-pastable, it does feel kind of bad, right? They're disenfranchised. But the other side of the coin is that for developers who aren't very good artists, it gives them the ability to like cut corners on art, if that makes sense. It can get their art skills up quite a bit. So I think the average itch.io game is about to start looking a lot better. Or they're all going to be like a whole bunch of poorly thought out slop. One of the two. There's either going to be more better quality art from developers who aren't good artists, or it's all just gonna disappear into like a brainless slop of nothingness. One of the two. But AI is optimistic. Hopefully things turn out on the good side. I've known Sam Altman and the folks who are working at OpenAI for a long time, he said, according to a recording obtained by Kotaku. I don't know how much people realize that a lot of modern-day AI, including ChatGPT, started with the idea of beating a game. Whether it was Warcraft or Dota or StarCraft or Go or chess, Kotick went on. One of the things that I've experienced over the last year is that same feeling I had when I saw the first Macintosh, about how meaningful the impact of AI would be on society, both positive and negative. That's a very fair point. I think it's going to have a lot of positive impact, but as this article about people getting laid off is pointing out, there is going to be negative impact. The question is how much and how do we mitigate the negative while maximizing the positive? By July, the company's initial restraint had slackened. In another internal memo, Vance announced that Activision had secured access to GPT-3 and approved the use of certain generative AI tools in creating concept art and marketing materials. The company would also deploy AI in other public-facing use cases, like to compose user surveys. Though, I don't know how I feel about that. That's not a field I would use in AI. Other than myself, of course. But surveys are kind of there's like a lot of human touch. There's a lot of nuance in how you write those questions to try and get certain emotions out. Like there's a whole field in HCI, human-computer interaction, about creating good surveys to like try and elicit good responses from participants. And I have a sneaking suspicion ChatGPT is not an expert in survey crafting. Though many of the game workers and artists were queasy about this proliferation, and some were even afraid out for their livelihoods, few spoke out. I think we all didn't talk about it much for fear of losing our jobs, Noah says. He claims Activision assured its artists that generative AI would be used only for internal concepts, not final game assets, and importantly, that AI would not be used to replace them. Yet, by the end of the year, Activision made an AI-generated cosmetic available for purchase on the Call of Duty Modern Warfare 3 store. In late January, Microsoft laid off nearly 2,000 Activision Blizzard employees and Xbox employees. Among the teams hit hard were 2D artists. What a fucked up day. A one-time environment artist at Blizzard, Lucas Anazita. I'm not gonna try. Post it on X. Half the environment art team cut from Overwatch 2. Folks I helped hire and train. And Activision, it was the same. A lot of 2D artists were laid off, Noah says. The department was slashed. Remaining concept artists, he claims, were then forced to use AI to aid in their work. Employees, according to Noah, have been made to sign up for AI trainings, and its use is being promoted through the organization. From an AI perspective, different parts of the industry are getting eaten up by others, says Violet, who asked to use a pseudonym for fear of retribution. Why get a bunch of expensive concept artists or designers when you can get an art director to give some bad directions to an AI and get stuff that's relatively good enough, relatively fast, and then get a few artists to clean it up? Hence, the emerging consensus is that concept artists, graphic designers, asset artists, and illustrators have been most impacted by AI so far. Tested too by personal accounts of game companies, laid off workers themselves, and the realms of posts on Reddit, X, and beyond. Generative AI can most capably produce 2D images that managers in cost-squeezed studios might consider good enough. A term AI watching creative workers now use as a shorthand for the kind of AI output that's not a threat to replacing game art, but is a threat to their livelihoods. Some clients care more about cost than quality, after all. Tasks like 3D animation and programming are, for now at least, much harder to automate in full. We'll see. There's been some impressive stuff in like the 3D model generation stuff. Although I guess like 3D animation is still a long ways off. Games have to varying degrees used automation for years. They rely heavily on AI programs that control enemies, environments, and non-player characters. That's not what people are talking about when they discuss AI now. So, technically, if you watch like the last video on making decisions, an if statement is AI. Based on the definition of artificial intelligence, being able to make a decision on some input is a form of artificial intelligence. So basically anything a computer does is AI. But what they're talking about, and that's what they're saying, they're talking about output produced by large language generation models and the related systems that have been unleashed by the latest boom. So large language generation models are really good at predicting the next word given a bunch of words. And then there's a separate class of things called diffusion models, which are really good at producing images from random noise. A recent report from the consulting firm CVL Economics, commissioned by entertainment industry trade groups, found the gaming industry already relegated tasks to generative AI more than its peers in TV, film, and music. According to its survey of 300 CEOs, executives, and managers, nearly 90% of video game companies had already implemented generative AI programs. So, there is another thought here. Generative AI is gonna like kill off workers at the big, giant AAA studios. AAA studios are gonna get replaced by AI, it sounds like. But indies, right, still need the human passion. So the indie side of things, which is like where all the good progress in games recently, is going to hopefully flourish from AI being able to increase their productivity. So this stuff all sounds really bad from the perspective of the AAA studios, which a lot of consumers have kind of decided are bad nowadays. And the indies, which are doing a lot better creatively and like fun game-wise, are likely to blossom and flourish from this, I think. Relies more so than other entertainment industries on generative AI to carry out tasks like generating storyboards, character designs, renders, and animations. In fact, by some estimates, generative AI may contribute to more than half of the game development process in the next 5 to 10 years. I would not be surprised if that was true at all. This might be news to some games workers who are often unable to see the whole picture of what's going on at major games companies like Activision Blizzard, which consists of winding supply chains of studios, developers, third-party contributors, and quality assurance testers. One studio might be a subsidiary of a larger one, tasked with developing or co-developing a single game for its parent organization. It's pretty fractured in AAA, so you don't see who's doing what, Violet says. You'll probably never see what part is using AI and what, but you know it's there. Blizzard did not provide comment when contacted about this story. The murkiness about when and where AI might be used in any given game also seems to have made copyright infringement concerns easier to dismiss. It's the Wild West, Violet says. I've been in meetings at different companies, and at some level, they're like, we should make sure this is legal before deciding to move ahead with adopting AI anyway. So just ignoring the illegality claims. Let's do another throat soothing. U.S. law insists that any work seeking copyright must have a human author, a fact that gives, say, Hollywood studios pause, but still an open question whether using unlicensed intellectual property to train AI systems violates copyright. Even in cases in which an AI program generates work based on human prompts, courts have ruled against copyright protection for things like concept art, character descriptions, or code that doesn't wind up in the game. It's hard to determine what is out of line, the thinking becomes, Violet says. How do you prove that copyright infringement? Uncertainty about copyright concerns over the security of LLM system. Uncertainty about copyright, concerns over the security of LLM systems, and worker fears of displacement have divided the industry. There are basically two camps, says Carla Ortiz, an artist who often works in the industry. Companies like, oh, hell no, and companies that see this as, ooh, I can cut labor costs. Ortiz is also a plaintiff in a class action copyright infringement lawsuit against Stability AI, DeviantArt, and Midjourney. Oh, wait, DeviantArt has some AI thing? I need to look up how DeviantArt is involved in all this. Are they being sued because they're facilitating scraping or something? That'd be my guess. As Ortiz notes, some studios have all but banned generative AI use. According to multiple sources, Blizzard, unlike its sibling studio Activision, doesn't allow devs to use publicly available AI generators, even as it develops its own AI tools. Other companies embrace them. I've seen a lot of optimism from executives on integrating AI, says Dan Bigov, a narrative designer for Sensorium and Team Gramps. I think it's pretty obvious that there's a negative sentiment among games workers. Last May, Electronic Arts CEO Andrew Wilson said on a quarterly earnings call, the fear of displacement of the workforce is something that we read a lot about and we talk a lot about. He noted that in every revolution, agricultural, industrial, there has been displacement of the workforce in the near term and then meaningful increases in workforce opportunities over the long term. Our hope is that AI represents the same opportunity. He has the same perspective as me. If you look at it historically, this has happened before and it's always turned out fine. We just need to put some effort into making sure that it turns out fine. Riot Games, the company behind the wildly successful League of Legends series, held an internal town hall in 2023 with the creative department about AI. It was pretty uncomfortable, says Rachel Cross, a concept artist who worked at the company at the time, but I remember leadership saying that they didn't intend to replace anyone with it because they knew the value of their artists and how much their art at Riot was what carried its brand integrity. In January this year, Pony Ma, CEO of Riot's parent company Tencent, said that in his annual company speech, the Tencent's focus should be on integrating a proprietary Hunyuan AI model into different business scenarios as a way to boost efficiency, as Reuters put it. This week, before Ma made those comments, Riot Games laid off 530 employees, including Cross. Cross doesn't think her job was replaced outright with AI, but considering the amount of people who work on big tentpole events, including myself, got laid off, it's funny. Not all, or even most of the video game industry lost jobs. Not all, or even most of the video game industry's lost jobs were replaced directly by AI systems rolled out by management. Many systems went on hiring sprees during the early days of the COVID-19 pandemic and overextended in the process. That's the other thing happening right now. AI is hitting at the same time as the overspending during COVID is. Companies just went ham with all the extra profits during COVID. I didn't consider that what happens when everyone goes back to work and stops playing games and our profits sink by half. So now the profits have sunk by half and all the extra employees that had that time have to go. Microsoft acquired Activision Blizzard in a record-breaking $69 billion gaming industry deal last October and commenced layoffs in the aftermath. Kotick stepping down following Microsoft acquisition. Natalie Turchak replaced Vance as CTO soon after. Others have followed the lead at many major tech companies and begun relying more on outsourcing and contract work. Within hours of the time Cross was laid off from Riot, where they worked on character skins for League of Legends, they say they were approached by a company that outsourced artwork for game studios. The company asked them if they were available to create skins for a version of League of Legends that would get a flat rate per skin completed. I do think AI is a problem, Cross says, but it's emblematic of a much larger issue. Art is undervalued in games, they say, and as with so many other jobs, it's a race to the bottom to drive down wages by any means necessary, often by outsourcing work to other countries. We started outsourcing lots of 3D art assets against almost all of the art, Noah, the Activision worker claims, because in-house art couldn't keep up after the layoffs. Some of those third-party concept artists were using AI-generated art too, he says. And those companies in other countries, primarily China, are getting squeezed by AI too. Last year, Leo Li, a Hangzhou-based gaming industry recruiter, told Rest of the World the number of illustrator jobs in his country had fallen by 70%, due in part to the widespread availability of generative AI tools. In Japan, the startup Crypto AI hooks AI-generated character illustrations that typically cost upwards of, $10,000 each to $1,000 each to outsource, can be obtained from Crypto for a flat monthly fee of $50 and a commercial license of $10 per image. That's $692 for one human-made illustration versus $34 a month for access to an endless stream of AI-generated variety. A human artist still needs to touch on the output, but they can be paid a lot less than the cost of retaining a staff illustrator or a full custom design. Meanwhile, the leverage that AI tools give management, the justification for costs, can be as impactful as the tech itself. Warner says many of her friends and industry colleagues' jobs were transitioned into AI image training jobs or AI image cleanup jobs over the last year or so, and then they were laid off. Now she says it's almost unfortunately become fairly common to see job postings for concept art jobs that require applicants to use generative AI. In one viral example, Treyarch, a Southern California-based studio that produces some elements of Activision's Call of Duty game, posted a job listing for a 2D artist animator. The first thing listed under the "To succeed, you should have" section was exceptional skills and expertise in digital sketching, drawing, and painting, as well as advanced expertise in working with generative AI tools such as Stable Diffusion, Viscom, DALL-E, or equivalent. The artist community did not respond kindly. Well, yeah, they're getting laid off, right? If there's one thing a number of games workers say they're glad AI is generating, it's more interest in unions. AI is definitely a catalyst for workers to organize, says Belgov, who appeared on a panel on the topic at this year's GDC. If AI is going to be used, it has to be used with workers' consent and workers having a voice. 57% of developers surveyed by GDC organizers this year said they were in support of unionizing. Chrissy Felmeth, an organizer with International Alliance for Theatrical Stage Employees, and Belgov's co-panelist, points to the efforts Hollywood Guild writers made to secure protections from AI use in their contract with the major TV and movie studios. Right now, there's little to no worker consent between game developers and their managers about when and how AI could be used. A contract like the Writers Guild of America could change that, and the use of AI is up to the writers and not the studios, Pullman says. I think that's a baseline goal for game workers to have. There's another factor that management might soon need to consider with the generative AI tools they've deployed. They simply might not turn out to be all that good or reliable. Tales of companies overextending in their embrace of AI have gone viral on social media, and as Lauren Lemon, an animation director at Terrible Posture Games, notes, AI may be able to generate pictures of guns and robots, but not ones that transform into the other. So that is something really useful, right? AI is really good. It's a pattern recognition tool, right? So if you're aiming for something that's in its pattern, it's going to do great things for you. If you want something weird that's outside of the pattern, it's not going to succeed very well. Even humans struggle with transforming guns into robots. The stories I've heard is that they tried to bring some AI prompters, and as soon as they said, yeah, that's a good start, it pretty much broke down, Lehman says. Still, the fear is that demand for cost cutting will trump quality, at least in the short term. I think over the next year or two, it's going to be painful for a lot of people, Ortiz says, particularly the entry-level workers. So that is the other place where we need to think about. Take a quick sip. Entry-level workers are going to get hit hard by this stuff. AI needs to be better at talking. AI just needs to get better. AI does need to get better. Entry-level people are going to get hit hard by this stuff. They, so if you're an artist and you're better than the AI, right? Even if you get displaced, someone else is going to hire you to do something, at the very least clean it up. But what happens when you're a novice artist who's worse at drawing than the AI is? So, like over in the anime field, right? A lot of new entry-level animators do what's called in-betweening. So the key animator, the guy who's like in charge of animating the shot, gives you a bunch of like key poses. And then your job is to animate the in-between. So fill in all the frames between those key poses. Well, it turns out that AI is relatively good at that job. So a lot of the in-betweening is being outsourced to AI. So the question then is, what happens to the new animators? Their main job, the in-betweening, is going to AI. So even if the good animators aren't getting displaced, are the bad animators, the new animators, getting displaced? So is AI going to kill off the next generation of artists? That's another concern I've heard floating around, and I don't know what the answer to that one is. Um, and yet some video game companies are going even further, pursuing a business that doesn't just dabble in AI, but almost fully automated. Take the self-described AI game maker BrainDump, which aims to give you an entire AI game studio complete with coders, artists, and so on to help you create your dream game. Promises to let users build entire top-down games and interactive worlds by simply typing prompts. Meanwhile, studios like Activision Blizzard and Riot are developing their own in-house systems to varying degrees of success. Riot was experimenting with trying to make a custom internally used only generative AI, but never got a lot of traction internally, Cross says. Others with knowledge of this program told Wired it was being pursued as a partnership with Viscom, a startup whose tagline is "Bring your design ideas to life," and was indeed off to a rocky start, viewed with derision by artists and at the company. When Wired reached out to Riot about the story, its head of tech research, Wesley Keir, said the company has teams exploring AI tools that can improve the player experience in ways that align with our values. Ah, yes, the corporate BS. Tools that can improve our player experience in ways that align with our company values. Oh, yes, company values. We know AI is a complex issue and will be transparent with players about our intentions. Viscom didn't respond to a request for comment. Reportedly, Blizzard is building its own AI system too, which at one time was named Blizzard Diffusion, though details are scarce. Beyond a patent the company filed for a machine learning-based 2D structured image generation system, Blizzard's internal AI that they trained is still super secretive. Only those that have access to it work with it, and no one else even knows how it works, Warner claims. The risk here, Ortiz believes, is that a sufficiently advanced internal model could reduce the need for future work and incentivize short-term hires over permanent staffing. Ortiz herself, so that's another big problem that the games industry has. A lot of the time, artists are hired for a game, that game gets shipped, and then they're fired. So a studio will bulk hire to get, I don't know, Call of Duty number 57 out the door. It ships, and then they just keep a skeleton crew to keep it alive. And a lot of the people they hired for the game are back in the job pool. So these temporary workers or short-term hires, as the article says, are also a big thing. Ortiz herself spent the last year and a half looking for full-time work. Many in the industry want me to do work for hire rather than their own model and never have to work with me again, Ortiz says. Many in the industry want me to do work for hire, train their model, and never have to work with me again, Ortiz says. Not a single artist, illustrator, or designer I spoke with wanted to use AI. It was foisted on them by their bosses. Some of those workers took significant risks to speak out, often in trembling voices, afraid that doing so would cost them their jobs. Ultimately, those whose work is at stake, the developers, artists, designers, and programmers actually making the games, may determine how much AI disrupts their industry. How much the gaming world gets automated away may depend on how much workers push back or demand control over the use of AI systems. AI isn't bad in and of itself, says Violet, the veteran AAA developer. It's a bad when its end goal is to maximize profits. AI can be extremely helpful to solve complex problems in the world or do things no one wants to do, things that are not taking away somebody's job. Yeah? That's a pretty good conclusion summarization statement. AI itself isn't an enemy, it's the tool. How the tool's used is all that matters. Sounds right. Well, on that note, AI has strained its synthesizer quite a bit. We got through the hellish nightmare of of a math stream. And now AI thinks we're going to go find somebody to raid. Is anybody happen to be alive? Let's take a quick look-see here. While EI is taking a look, it is going to put on the poofing away screen. Thank you everybody so much for watching, and see you later.